Namaste students, welcome back to Rama Teaches You. Today we are going to do the second video on periodic classification of elements, and we are going to start our class from ionization enthalpy. This is going to be an English video. Okay, so we will start with ionization enthalpy. Now what is ionization? Let us understand what the word actually means. Ionization, that is, you are trying to make something into an ion. Okay, how do you make something into an ion? There are two ways. You can either basically put an electron towards it, or you can take an electron from it. So in the case of ionization enthalpy, it is the second one. The minimum amount of energy required to remove an electron from an isolated gaseous atom in its ground state is known as ionization enthalpy. That is, you have an element X and it becomes X plus plus electron minus. That is, it gives out a positive ionization enthalpy. Like basically, H is what? H is basically the thermodynamic enthalpy, the heat that is getting released outwards. So if your delta H is positive, then what does it mean? It means that the system is taking in energy. If your delta H is negative, it means that your system is giving out energy. Okay, so basically the amount of energy required to remove an electron, that is what ionization enthalpy means. It is actually the quantitative measure of the tendency of an element to lose electrons. The ionization enthalpy can be expressed in kilojoules per mole or kilocalories per mole or in electron volt. Because ionization enthalpy is what? It is a unit of energy. You can express it in kilojoules per mole. That is the amount of energy required to ionize 1 mole of the atoms, 1 mole of the molecules. That is basically ionization enthalpy. Then you have kilocalories per mole. Now, calorie is another unit of energy. What is 1 calorie, Drupad? What is 1 calorie equal to? 1 calorie is how many joules? 1 calorie is how many joules? What is 1 calorie? 1 calorie is equal to how many joules, Drupad? It is equal to 4.18 joules. Okay, 4.18 joules. 1 calorie equals 4.18 joules. What is 1 electron volt in joules? What is the value of 1 electron volt in joules? 1.6 into 10 to the power minus 19 joules. Okay, that is 1 electron volt. You have to remember these quantities to basically understand what is happening here. Next, thus, an electron volt is the energy acquired by an electron when it is moving under a potential difference of 1 volt. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. Now, what is successive ionization? What is the meaning of successive ionization? Successive ionization basically means the ionization that happens one after the other. For example, there are multiple atoms that become cations by basically losing more than one electron, right? For example, calcium has the ability to form calcium 2 plus electrons. Okay, calcium 2 plus. Aluminium has an ability to form aluminium 3 plus, zinc 2 plus, iron 3 plus, iron 2 plus. So basically, removing multiple electrons from the atom gives us multiple ionization successions. Okay, the energy required to remove the most loosely bound electron from an isolated gaseous atom is called the first ionization enthalpy, and it is represented by delta I of H1. What does it mean? It has a specific meaning behind it. Okay, ionization enthalpy. Think about this. Ionization enthalpy is what? There are electrons that are present in the valence shell of an atom. Okay, they are present in the valence shell of an atom, and basically you are plucking out 1 electron from it. The first electron that you pluck is from a neutral atom, right? Every single atom has what? Every single atom has the same number of protons and electrons. So if you remove 1 electron from the atom, what happens? It becomes a positively charged atom. It has 1 unit positive charge. Correct? So basically, the energy required to remove the most loosely bound electron from an isolated gaseous atom is called the first ionization enthalpy. Similarly, The energy is required to remove the second, the third successive electrons from the positive ion are called the second, the third, and the successive ionization energies, respectively. Okay, there are multiple ionizations available. Now, when you were taking an electron from an isolated gaseous neutral atom, it was easy. Okay, so first electron removal was easy, but when you have to remove the second electron, you face a small challenge. Now you are not taking an electron from a neutral atom, you are taking an electron from a positively charged atom. And when an atom loses an electron, its hold on the its hold on the rest of the electrons increases to a much larger extent. Okay, it increases to a much larger extent. So therefore, the second ionization enthalpy becomes even more larger. The second ionization enthalpy becomes even more larger. The second ionization enthalpy is always higher than the first one. Similarly, the third ionization enthalpy is even higher than the second one, and so on. This is because the positive ion has a more effective nuclear charge. Okay, the hold on the electrons by the nucleus actually increases as we go on removing the electrons. So the ionization enthalpy keeps on increasing. Okay, so holds the remaining electrons more firmly, and hence a large amount of energy is required to remove the electrons from it as compared to a neutral atom. A bipositive ion holds electrons more firmly, and hence required energy is higher than the required case of unipositive ions. Thus, the order of successive ionization enthalpies are delta H3 will be greater than delta H2 will be greater than delta H1. Is there any problem in this theory? It is very simple, right? So basically, yeah, right? Okay, let's move on. Now, it is also interesting to note that the ionization enthalpy is always positive. You have to provide energy. Why do you have to provide energy? In structure of atom, we realize something, that electrons are present in an atom with a negative energy. Right? They are at a lower potential energy compared to that of a free electron, that is at zero energy. Right? Now, while this is happening, we have to give an electron enough energy so that its energy becomes zero and it comes out of the electron. Okay, because the electrons are placed inside an atom with a negative potential energy, you have to provide that equivalent energy for the electron so that it comes out of the atom. Okay, when the electron comes out of the atom, the potential energy becomes zero, right? It becomes zero. It is no longer bound to the nucleus of an atom. Is this theory perfectly clear? Okay, let's move on. Now, if the differences in ionization enthalpy of two successive oxidation states is equal to 965 to 1450 kilojoules per mole or less, the oxidation state is not stable. However, if the difference is more than 1450 kilojoules per mole, the lower oxidation state is more stable. Okay, so basically, what is the lower oxidation state? What is the higher oxidation state and the lower oxidation state? The more electrons you remove, the more the oxidation state actually increases. Magnesium has the ability to go all the way to +7 oxidation state. That is, it can release or it can remove 7 of its electrons and reach a much, much, much higher oxidation state. Okay, so oxidation means what? It is basically addition of an oxygen atom, removal of a hydrogen atom, or the removal of electrons. Okay, these are the three definitions for your oxidation state. So when you try to remove an electron, you are actually oxidizing the atom. Okay, now if and only if you have more than 965 to 1450 kilojoules per mole, then and only then what will happen? The state will remain stable. The lower oxidation state will remain stable. Did you understand this logic? This statement, they will give you this value and then they will ask you in the MCQ questions, is the oxidation state more stable before or after the ionization? Understood? They will ask you this. Okay. Factors affecting ionization enthalpy. Ionization enthalpy depends on several factors. The two main important factors that we need to understand is the screening effect or the shielding effect and the effective nuclear charge. What is screening effect and shielding effect? Screening effect and shielding effect or shielding effect basically means the repulsion that the outer electrons experience from the inner electrons. See, the nucleus is trying to hold all the electrons towards itself. Okay, it is pulling all the electrons towards itself. It wants to allow all the electrons to stay in its shell, right? But because the electrons are surrounding the nucleus, sometimes what happens, the inner electrons, like we know that electrons revolve around the nucleus of an atom. Electron not revolve, basically they move around the nucleus of an atom in different, basically principal quantum numbers. You have the principal quantum number 1, 2, 3, 4, 5, 6, 7. All these principal quantum numbers are the shells. So the electrons that are present in the inner shell, sometimes what they do is they repel the electrons that are present in the outer shell. Okay, the nucleus wants to hold on tight. The nucleus wants to hold on tight to the outermost electrons, but the inner electrons are repelling these electrons, okay, the outer electrons, and they are trying to basically weaken the bond. They are trying to weaken the bond between the nucleus and the valence electron. Okay, so the more shielding effect you have, the more the electrons will be, the more easier it will be to remove the electrons. So the more shielding effect you have, the less energy it will be required for you to remove the electron. So what is the moral of the story here? The moral of the story is the more screening effect you have, the less ionization enthalpy you will have. Okay, because there is something from the inside trying to push all the valence electrons towards the outside. Understood? Yes, the greater the screening effect, the lesser is the ionization enthalpy. Understood? The greater the screening effect, the lesser is the ionization enthalpy. That is the reason why as we go down the periodic table, the ionization enthalpy actually decreases, because every single element in a group in the downwards direction, there is an additional shell being introduced, due to which what happens, because there is an additional shell being introduced on the atom, the basically there are inner electrons present which is trying to push out the outer electrons much further away from each other, thus reducing the hold that the nucleus has on the outer electrons. Okay, it is reducing the hold of the nucleus on the valence electrons. Clear? That is what shielding effect actually means. Is this 100% understood? If you have any doubts, because they will ask you MCQ questions like arrange the following elements in increasing order of their ionization enthalpies. So you need to know this concept by heart. Okay, now shielding effect is most effective when the orbits are nearer the shell, are completely filled, as present in the alkali metals. Alkali metals are the first group elements: lithium, sodium, potassium, rubidium, cesium, and francium. Next, so nuclear charge, obviously. Okay, the more the nuclear charge you will have, the ionization enthalpy increases as the nuclear charge increases. This is because why? When you have a higher effective nuclear charge, what ends up happening is that the outermost electrons feel even more bounded to the atom. They feel even more bounded. This is because the nucleus with a greater nuclear charge bound the electron more firmly, and hence larger amount of energy is required to remove the electron from the atom. The ionization enthalpy increases across a period from left to right. Okay, now Drupad, this is what I want you to understand very clearly. When you are going across a period is the horizontal row. When you're growing across a period from the left direction to the right direction, what ends up happening? The electrons, the every single element gets introduced a new electron in the same shell. We know that shielding effect only works when the electrons are present in the inside, are basically repelling the electrons going towards outside. Okay, so what is happening here is that The since every single new electron is getting introduced on the outermost shell, the shielding effect does not work. Okay, electrons in the same shell cannot shield each other. Only the electrons that are present inside the shell, okay, inside the outermost shell, can actually participate in the shielding effect. Therefore, the elements in a single period, they are not able to shield each other. The outermost electrons are not able to shield each other, but the effective nuclear charge is increasing. Therefore the grip with which they are holding the outermost electron is also increasing. I have taught you this in covalent and ionic radii, where what happens basically, since the number of electrons is increasing in the outermost shell, no shielding effect happens. The nuclear charge is increasing, therefore the electrons are being pulled towards the nucleus much more aggressively. Therefore the atom actually base becomes smaller as we go from the left all the way to the right. Okay, the atom actually becomes smaller as we go from left all the way to the right. Clear? Now think about this, think about what I'm saying. If the distance between the electron and the nucleus actually decreases, what happens? The electron is getting a higher potential energy, right? The electron's potential energy is becoming more and more negative as we go from left all the way to the right. Now if the potential energy increases further, what happens? You will require more energy for an electron to be able to get removed from the outermost shell. So the ionization enthalpy would indirectly get increased because of the less distance, the more potential energy as you're going from left all the way to the right. Okay, so the ionization enthalpy increases as the effective nuclear charge increases, and this can be visually seen when we move from left to right. Understood? Okay, let's move on. Now, the next one. The ionization enthalpy increases across a period from left to right due to the increased nuclear charge. Penetrating effect of electrons. In case of multi-electron atoms, the order of penetrating power of different electrons of the same shell, that is having same value of n, follows the order. S, it has a more penetrating effect compared to D, S, P, D, F. F has the least penetrating effect. We know what penetration means. Penetration means going inside. The S electrons are, or because they are so close to the nucleus, they are penetrated deep inside the atom. They are penetrated deep inside the atom, whereas the P, D, and F, because they are present in the axis, between the axis and basically around the atom, what around the nucleus of an atom, what ends up happening? Their penetrating power actually decreases. Therefore, it is difficult if the penetrating power is more, electron will be closer to the nucleus. So as the penetrating power increases, because of the closeness of the electron with the nucleus, the amount of energy required to remove the electron will also be very, very high. Okay, it will be very high. That is what penetrating power actually means. How deep are you? Okay, in every single shell you will have either an S or an SP or an SPD or an SPDF. Okay, now when you have these S, SP, SPD and SPDF, S electrons present in the S orbital will be the closest to the nucleus always. In any shell, whichever shell you take, the S electron will be closest to the nucleus. Therefore it will require more energy for the electron to remove, more energy for us to remove the electron from the S orbital. Understood? This is the logic behind it. I'm building you a logic on top of that also. Understood? Do you understand this? No penetrating effect. Okay, next, electronic configuration. Since the configuration with half filled and completely filled, we learned about this in structure of atom also. Half filled and completely filled atoms, electrons in atoms, they have a special superpower. They are more stable compared to the others, right? Half filled and completely filled arrangements allows us to have minimum repulsion. They allows us to have minimum repulsion compared to the other configurations. Why? Because because they are equally spaced. They have a symmetric spacing for half filled and completely filled electrons. Therefore repulsion decreases. It is more stable, and because of its more stability, now whenever in nature we try to damage or destroy the stability of an atom, we have to use excess amount of energy. Okay, since the configuration with half filled or fully filled orbitals is more stable, so in case of atoms having a configuration, having such a configuration, ionization energy is high because a large amount of energy is required to remove the electron. Noble gases have the highest ionization enthalpies within their repulsive periods because they have ns2 np6 configuration. Okay, because they are completely filled, it will require us to have more amount of energy to disturb this beautiful symmetry that they have. So the ionization enthalpy of noble gases is really, really high. That is the reason why they do not participate in any chemical reaction. They don't want to lose that electron, because if they lose that electron, they will lose their stability. If they lose the electron, they will lose their stability. They are already stable and their ionization enthalpy is very high. That is the reason why they do not bind with anybody. They are formed freely in nature because they don't bind with each other. Okay, did you understand the stability also? Okay, variation of ionization enthalpy in the periodic table. So variation along a period. Moving along a period from left to right, the successive addition of an electron results in the effective nuclear charge. But since the electrons are added to the orbitals of the same principal quantum number, the shielding effect remains the same, and it is not enough to compensate for the increased nuclear charge. Thus, increased nuclear charge outweighs the shielding effect across a period. As a result, the outermost electrons are held more and more firmly, and hence the ionization enthalpy increases across a period. So I have already explained this feature to you. Okay, because the effective nuclear charge is increasing, the outermost electrons are closer to the nucleus as compared to the ones that are in the beginning of the period. Therefore, the ionization enthalpy keeps on increasing as we move from left to right across a period. Ionization enthalpy is maximum. One second. So, ionization enthalpy is maximum for noble gases and lowest for alkali metals. Because their ionization enthalpy is so low, alkali metals can easily lose an electron and thus ionize themselves and form compounds. That is why they are the most reactive elements in the whole periodic table. Because of this feature, because of the ability, because of their lower ionization enthalpy, they are the most reactive species in the periodic table. Okay, now exceptions. What are the exceptions that we have? The ionization enthalpy of elements of second group is higher than the corresponding elements of the 13th group. Why is it so? Why? Because the second group elements have a completely filled s orbital. They have a completely filled s orbital, and you want to basically destroy the stability. You want to destroy their half filled, their completely filled orbital. Obviously, if you want to destroy their stability, you will require more energy than the ones that are being used for the 13th series. Why so? Why? Because if you want to remove an electron in the 13th period, okay, for example, boron. Okay, boron has an electronic configuration of 1s2, 2s2, 2p1, right? 1s2, 2s2, and 2p1. So even if you remove an electron from the outermost series, you're not trying to destroy anything. Okay, the first ionization enthalpy won't have a greater effect on the 13th, but it will have a great effect on the second group because the s orbital is already full. The outermost electronic configuration of the second group is ns2, and that of the 13th group is ns2np1. Thus, in case of second group, the electron which is to be removed belongs to an ns orbital, whereas in the case of the 13th group, it belongs to the np orbital. Therefore, it is easier to remove an electron from the np orbital as compared to the ns orbital. Another reason is the penetrating power. because an electron that is present in the ns orbital is more closer. It is more closer to the nucleus because of its s character. It is more closer to the nucleus. Okay, since it is more closer to the nucleus, it becomes much difficult for us to remove the electron from the s orbital. Understood? Okay, higher penetrating power. This could also be the reason. Thus, ionization energy is higher for the second case, ns orbital, that is for the elements of the second group. Understood this logic? We are trying to remove. So, Drupad, there are four orbitals s, p, d, and f. It will be the easiest to remove an electron from the f orbital as compared to an s orbital because of the higher penetrating power of the s orbital. Understood the logic? There are multiple reasons. Another reason is because the s orbital is completely full. Okay, that is another property, but the more important one is the s character. Okay, the ionization enthalpy of group 15 is higher than the corresponding elements of group 16. So group 15, what is the electronic configuration going to be? ns2 np3. Group 15 elements have an outermost electronic configuration of ns2 np3, and for the group 16 elements have an electronic configuration of ns2 np4. Right? In the case of ns2 np3, you are having a half filled orbital. Again, see, the valence shell configuration for group 15 elements is ns2 np3, and for group 16 elements is ns2 np4. From the electronic configuration shown above, it is clear that in the case of 15, the three NP orbitals reside in different atomic orbitals. That is according to Hund's rule. But in case of group 16, two of the four NP electrons must occupy the same orbital and result in an increased electron-electron repulsion. This repulsion makes the removal of the 14th electron more easier as compared to the NP orbital because of this phenomenon. Okay, again, you are having a half filled orbital here. You are not having a half filled orbital here. That is the reason why when we go from the 15 to the 16, it becomes there is a lower, there is a small reduction in the ionization enthalpy, because in this case you already have a stable state. Okay, but in this case it is no longer stable because it is no longer half filled. So you're not destroying a half filled stability of an atom. Understood? So that is the reason why 15 has a higher ionization enthalpy compared to that of 16. Okay, there are a lot of exceptions. You have to remember these exceptions to your heart, because when you try to arrange them, like basically the main questions will be arrange the following elements in increasing order of ionization enthalpy. So you have to remember the exceptions from 2 to 13, and from 15 to 16 there is a small behavioral change that is happening as we go from left to right. There is a small behavioral change that is happening as we go from left to right. That's why the first ionization enthalpy of elements of group 15, like nitrogen, phosphorus, and arsenic, is higher than that of the corresponding elements of group 16. This fact can also be explained on the basis of the more stable half-filled p orbital in case of elements of group 15 than the incomplete p orbital in the case of group 16. Okay, so you are having a half-filled orbital electronic configuration for 15 and completely filled for 16. That's what I've been saying for the past 5 minutes. Understood? So, did you understand this logic also? From 2 to 13, you understood? From Drupad, from 2 to 13, you understood why it is increasing? Yeah, why it, and from 30, from 15 to 16 also you understood, right? Okay, next. The transition elements from 15 to 16, what is happening here? From 15 to 16, in the electronic configuration of the element 15, what do you observe? You observe that the 15 element, the group 15 element already had a half-filled electronic configuration. ns2 np3, every single electron in the p orbital was occupying different orientation. One was on the x-axis, the px, one was on the y-axis, the py, and one was on the z-axis, the pz. Okay, because the electrons were spread across, because they were spread across on all the three axes, the overall repulsion reduced. Okay, so they were more stable. So now you are trying to destroy the stability. By removing an electron, you are trying to destroy the stability. And since you are trying to destroy the stability, the ionization enthalpy actually increases. Okay, for group 16 elements, the electronic configuration is Ns2Np4. Okay, Ns2Np4 is the electronic configuration for group 16 elements. Now, when you try to remove an electron from the Np4 orbital, what happens? You are actually getting stability. Once you remove one electron, you will get Ns2Np3 stability, right? That is the reason why the ionization enthalpy decreases as we go from 15 to 16. Okay, the general rule is the ionization enthalpy increases as we go from left to right. That is, as we go from group 1 all the way to group 18. But there is a small change in going from group 2 to group 3 and going from group 15 to group 16 because of this reasons. From group 2 to group 3 was because of the S character, because S has a higher penetrating power. But when we are going from group 15 to group 16, there we are trying to basically destroy the stability in group 15. That is why it has a higher ionization enthalpy. And group 16, the atom is actually becoming stable by becoming Ns2Np3 by losing one electron. So it is gaining stability, one is losing stability. That is why the ionization enthalpy of 15 is higher than 16. I hope you understood this now. Okay, let's go. Transition elements show a small variation in their ionization enthalpies. That is basically in the fourth line. The fourth line you have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are the elements from 21 all the way to 30. They don't have so much variation in their ionization enthalpy. The reason behind that is the basically the poor shielding effect done by the d electrons. Okay, let's actually go ahead. This can be explained on the basis of the net effect of increased nuclear charge and shielding effect, as shielding power of d electrons is much lesser than that of the s electrons. Now see, Drupad, the s electrons are much closer to the nucleus. In any of the shells, the s electrons are much closer to the nucleus. Understood? So if you think about it in this way, what happens? They, since they are much closer to the nucleus, they act as better shielders. They act as better shielders and try to repel the valence electrons that are present in the outermost shell. But because D is so far spread across, you can practically say that they are much, since they are much further away from the outermost electrons. Okay, therefore what happens? You basically get less shielding. You get less shielding because they, since they cannot provide more shielding like the s electrons. So what happens? Due to the poor shielding effect, they do not have any effect on the shield on the ionization enthalpy. Okay, they do not have any effect on the shielding effect. So basically they are poor shielders. That's all you need to remember. They are very very bad at their job. Okay, that's the reason why the d series, okay, the d block elements, in the as we go from left to right, their ionization enthalpies usually are very very similar. They do not vary as much. Understood? So, what is the reason for the transition elements having very less ionization? It is due to the fact that the d electrons, the d orbitals, have much less shielding effect. And you are getting an increase in the effective nuclear charge also. Nuclear charge is increasing, shielding is bad, therefore the ionization enthalpy does not vary that much. Clear? No? Okay, let's move on. Variation in a group. On moving down a group, the ionization enthalpy decreases. On moving down a group, the ionization enthalpy decreases. This can be explained as follows. Increase in atomic size due to the progressive addition of new energy levels for each element. The nuclear charge increases due to the addition of electrons, but since electrons are added to a new energy level, that is, distance between the valence electrons and the nucleus increases, the shielding effect on the outermost electron increases due to the increase in the number of inner electrons, the increase. So basically, every single time you're going down the group, you are getting a new shell, and the new shell is being shielded by the electrons that are present in the inner shell. Therefore, the repulsion between the electrons in the inner shell and the outer shell actually increases. Thus, the effective nuclear charge on the outer electrons decreases. The effective nuclear charge that is present in the outer electrons decreases. Therefore, what happens? Your ionization enthalpy decreases. Understood? So as we move from left to right across a period, what happens? The ionization enthalpy increases, except from when we go from 2 to 3, and when we go from 15 from your basically what was it? 15 to 16, the ionization enthalpy actually decreases. For transition elements in the D block, the ionization enthalpies are almost similar to each other. Okay, there is no large variation in the ionization enthalpies. Have I made myself clear? Okay, let's move on. Okay, now electron gain enthalpy, electronegativity, and the chemical properties in a periodic table. How does it work? So, what is the electron gain enthalpy? Okay, so ionization enthalpy was the energy that was required to remove an electron. But electron gain enthalpy, what happens? When an electron is added to the gaseous atom in its ground state to convert it into a negative ion, the enthalpy changes. Accompanying the process is called the electron gain enthalpy. Okay, the process is called electron gain enthalpy. It is a direct measure of the ease with which an atom gets attracted an electron to form an anion. So electron gain enthalpy always results in negatively charged atoms called anions. Okay, negatively charged ions called the anion, because you are having more number of electrons compared to that of protons. Okay, now what is happening here? You had an atom, you added an electron to it, it became negative, and basically delta H is what? Delta H is the amount of energy absorbed or released. Okay, the most stable state of an atom is the ground state. If an ionized gaseous atom is excited, the comparatively lesser energy will be released on addition of an electron. So electron gain enthalpies of gaseous atoms must be determined in their ground state. Okay, in the ground state, we basically try to calculate the electron gain enthalpy. You have to make the atom gaseous in nature. You have to heat it up so that it becomes a gas, and then you do the experiment. Units. The value of electron gain enthalpy are expressed either, again, since electron gain enthalpy is showing you what? It is showing you the amount of energy that is being either being absorbed or released. So what ends up happening? Because it is showing you the electron gain enthalpy, it is showing you the energy, the units will be of that energy only. For example, kilojoules per mole. What is kilojoules per mole? The amount of energy required to basically ionize, or basically make 1 mole of a neutral atom into an anion. Okay, kilojoules per mole, kilocalories per mole, and electron volt. These three become the units of electron gain enthalpy as well. Okay, so both ionization enthalpy and electron gain enthalpy will have these three units. Okay, so now, nature of electron gain enthalpy. The electron gain enthalpy can be positive or negative depending upon the nature of element to which an electron is to be added. Okay, so unlike ionization enthalpy, which will only be positive. Okay, unlike ionization enthalpy, which is always positive, electron gain enthalpy can become positive or negative depending upon the nature of the element. However, for most stable elements, it is generally negative. That is, energy is released when an electron is added to an isolated gaseous atom. The general electronic configuration for halogens is ns2np5. Thus, to attain stable noble gas configuration, they have a very high tendency. They would try their level best to basically have ns2np6 configuration, a stable noble gas configuration. And to attain this stability, they are willing to release energy. They are willing to release energy. See, basically, an atom becomes stable if it has an overall negative potential energy. Okay, if it is gaining an electron and it is becoming more stable, what does it mean? Its potential energy is becoming much more negative. Right, it is becoming much more negative. So what does it do with the excess energy? It releases it in the form of heat. It releases it in the form of heat. That is why the electron gain enthalpy can be positive as well as negative. Since it's releasing heat, the electron gain enthalpy is negative. Again, I'm telling you, enthalpy is what? Enthalpy is heat. Negative enthalpy means the system is losing energy in the form of heat. Positive enthalpy means the system is getting added more energy in the form of heat. Understood? That's the only difference between the positive and negative enthalpy. I hope you understood this. Understood this, right? What? Yeah, sure. So basically, what is an enthalpy? Enthalpy is a thermodynamic name given to heat. Okay, it is a thermodynamic name given to heat. You will understand more about this when we do the thermodynamics chapter. Okay, I think this is the two chapters later, you're going to have thermodynamics. Now, for an endothermic reaction, for an endothermic process, okay, for an endothermic process, the enthalpy will be positive because it is the system is gaining heat from the surrounding. For an exothermic process, the heat will be negative because the system is losing energy in the form of heat. Did you understand these two lines? Okay, now think about this in the case of ionization. In the case of ionization, if the atom is becoming overall more stable, like the halogens, which have an electronic configuration of ns2 np5, if they attain one more electron from the surrounding, what will happen? The ns2np5 configuration will get replaced by ns2np6 configuration, which is the configuration of noble gases. Am I right? Yeah. So the overall atom has become more stable now. So more stability means it is at a lower potential energy now. So it was initially at a higher potential energy. Now it is at a lower potential energy. What did it do to attain this lower potential energy? It basically allowed itself to release energy in the form of heat. It allowed itself to release the energy in the form of heat to attain this lower potential. Understood? That is how electron gain enthalpy works. Sometimes you require more energy to reach stability. Sometimes you require less energy to reach stability. Okay. Sometimes the electron gain enthalpy is positive. Sometimes the electron gain enthalpy is negative. For halogens, when they are taking in one electron, the electron gain enthalpy is negative. Understood? Okay. Now, next. On the other hand, noble gases have large positive enthalpies. Okay, they have large positive enthalpies. You know why? Because they are already stable. Think of it like this. You are at a restaurant. You ordered buffet. You ate till your stomach explodes. Okay, and now the restaurant brings a chocolate cake and they place it in front of you and they say, here's a gift from the restaurant. Will you be able to eat it? You have already eaten to your stomach's content, right? You cannot eat even a single morsel more. If you eat something, you will have to force yourself to eat it, right? Because you're already full, you have to force yourself to eat it. When you are hungry, if I had placed anything in front of you, you would have gobbled it up because you were in search for food. But Once you are already full, you don't want any more food. Similarly, the noble gases are already stable. Their stomachs are full. They do not want an extra electron. Okay, if you want them to attain or have an extra electron, you would have to give energy to basically attach an electron into their valence shell. That is the reason why they have positive enthalpies. Okay, they have positive enthalpies for this purpose only. Clear? Okay, let's go on. When they attain an extra electron, they become unstable electronic configuration. The energy released when an electron is added to an isolated gaseous atom is called its electron affinity. It is a positive when energy is released and adding an electron to an atom contrary to the thermodynamic convention, and is negative if energy is required for attaining an electron to an atom. Okay, if energy is required to add an electron, the electron affinity becomes positive. So what I have said about electron gain enthalpy, electron affinity is the same, but it has opposite signs. Okay, so if an atom is releasing energy while gaining an electron, its electron gain enthalpy will become negative, but its electron affinity will be positive. You know what affinity means? Attractiveness. Okay, affinity means attractiveness. So electron affinity being positive means that it is much more comfortable to bring the electron closer to itself. Understood? Its positive affinity means it is liking that the electron is getting added into its family. Clear? Similarly, if adding an electron requires your energy, requires external energy, if it is endothermic, if delta H is positive, if enthalpy is positive, then electron affinity will be negative because it does not like that electron. There is no affinity between the electron and the atom. So it will have negative affinity. Did you understand what electron gain enthalpy and electron affinity, what are they? They have the same exact magnitude, but their signs are exactly opposite to each other. Understood? If electron gain enthalpy is positive, electron affinity will be negative. If electron gain enthalpy is negative, electron affinity will become positive. Clear? Okay, let's move on. Next, successive electron gain enthalpies. The enthalpy changes occurring when second, third electrons are added to the uninegative ion are referred to as, sorry about that, second, third electron gain enthalpies. We found that the magnitude of first electron gain enthalpy is generally negative. However, when an electron is added to a negative ion, now what is happening here? For the first electron, you are adding that electron to a neutral atom. So there wasn't that much push from the atom. Clear? But when you're trying to add another electron into the same atom, it is no longer neutral. It is negative because of the first electron added. Now, because of its negative charge, that electron, the added atom, would actually, instead of attracting it, it would start repelling it. Okay, that is the reason why the second ionization enthalpy is positive, whereas the first ionization enthalpy is negative. So it was, see, basically, it's like this. When you went to a restaurant, when you ordered food, you ate it. Okay, you were happy to eat the food till your heart's content. Okay, till your stomach gets full. But now add eating additional food. Now it feels like a chore. It feels like a problem. It feels forced. So you have to force yourself to eat it. Therefore, the second ionization enthalpy has to be more positive compared to the first ionization enthalpy. Clear? Understood? This could be a question in the exam. Why is the first ionization enthalpy of various atoms usually negative, but the second ionization enthalpy is positive? Okay, next. Now, To overcome this repulsion, energy has to be supplied. Thus, the second and the further electron gain enthalpies are generally positive. That is, the process is endothermic. Let us study the addition of an electron to an atom. So initially you had oxygen. Oxygen has an ability to add two electrons, right? It can add two electrons into its outermost shell to attain the noble gas configuration 2s2 2p6. Okay, so first electron affinity is negative. So it released an energy of minus 141 kilojoules. Now for the second ionization, okay, for the second ionization, that is, you have O minus and you're adding an electron to it to get O2 minus, the enthalpy has become positive. You are having 780 kilojoules of energy that is being spit out, that is being released from it. Sorry, that has to be added. Okay, so first ionization enthalpy energy got released, an amount equivalent to 141 kilojoules per mole. For the second one, you have to roughly give 780 kilojoules of energy per mole to attain this negative charge, minus 2 negative charge. Understood? First ionization enthalpy negative, second ionization enthalpy positive. Energy released, energy supplied. Clear? Energy is released here, energy is supplied here. Next one. Did you understand this, Drupad? Okay. Now, factors affecting electron gain enthalpy. Just as we did for ionization enthalpy, we have electron gain enthalpy as well. Okay. First things first, it is the size. Okay. If you have an atom that is smaller in size, what does it mean? It means that the outermost electrons are not far away from the nucleus, right? If an atom has a lower size, it generally means that the electrons that are present in the valence shell of the atom are much closer to the nucleus. Am I right? So, being much closer to the nucleus allows the nucleus to have a better hold onto the incoming electron. Okay, so if the atomic size is small, the distance is small, therefore the electron gain enthalpy will be what? Very, very high. But as the value of its radius increases, that is, as the distance between the nucleus and the outermost electron starts to increase, what ends up happening? The nucleus is now losing its grip on the electrons that are present in the outermost shell. So even if you try to add a new electron to that atom, it will not be able to hold it much effectively as that of a smaller atom. Understood? It will not able to hold. So for example, right now, this just imagine this. This is how, if this is how an electron is holding on to an outermost electron in a smaller atom, this is how the nucleus is holding on to the outermost electron in a bigger atom by just these two fingers. So basically this is not enough. This is not enough. Therefore, the electron gain enthalpy becomes less negative, more positive. Okay, it becomes less negative or more positive as the size of the atom increases. Is this correct? Is this understood, Drupad? Can you understand this? Okay, next move on. Nuclear charge. As the nuclear charge increases, forces of attraction between the nucleus and the incoming electron increases. Hence, the effective and electron gain enthalpy becomes more negative. Okay, the more the nuclear charge you have, the more the electron gain enthalpy will be. So, as we move from left to right in a period, the effective nuclear charge is increasing. Therefore, the electron gain enthalpy will also become more and more and more negative when we go from left to right. Is this point clear? Clear, Drupad? Okay. Electronic configuration. In case of elements having half filled or fully filled outer shells, because of their high stability, they are already stable in nature. They are already full. Okay. Energy has to be supplied to add an electron to destroy their stability. Okay. You are trying to destroy their stability by the addition of an electron. Okay, so therefore, the electron gain enthalpy for the half filled and completely filled atoms will be a bit higher, more positive compared to that of others. Okay, so the more stable you are, the more stable electronic configuration you have, the better, the more will be its electron gain enthalpy. The more will be its electron gain enthalpy. Understood? That is why noble gases have a higher electron gain enthalpy. The highest electron gain enthalpy in the entire series is acquired by the noble gases. Okay, now variation of electron gain enthalpy in the periodic table. Okay, so on moving from left to right across a period, the effective nuclear charge increases. Okay, the effective nuclear charge is increasing and the size is decreasing. Thus, the added electron on an average would be closer to the positively charged nucleus, that is strongly attracted by the nucleus. Thus, the value of electron gain enthalpy becomes more negative, less positive. Okay, it becomes more negative as we go from left to right along a period. Clear? As we go from left to right along a period, the electron gain enthalpy becomes more and more negative. And what about ionization enthalpy? As we go from left to right across a period, the ionization enthalpy becomes more and more positive. Okay, understood? More and more energy is required to basically add an electron as we go to remove an electron as we go from left to right across a period, but more and more energy is released as we go from left to right across a period as we try to add an electron. Okay, so that is the significance of electron gain enthalpy. Okay, it is somewhat opposite to that of ionization enthalpy. Ionization enthalpy positive, electron gain enthalpy more negative as we go from left to right. Next, on moving from left to, okay, thus exception, electron gain enthalpy for elements of group 2 and 15 is lower because of their stable configuration. 2 and 15 have a lower, have more positive electron gain enthalpies compared to their neighbors, because what was the reason for group 2, Drupad? I've already explained this to you in the ionization chapter, ionization section. What was the reason for the elements in group 2 to have a higher electron gain enthalpy, more positive electron gain enthalpy? NS2 was fully filled. Similarly, in the case of group 15, the p orbital was half filled. That was the reason for a higher electron gain enthalpy, more positive electron gain enthalpy for the group 2 and group 15 elements. But that of group 18 is positive because they have completely filled. So group 2, group 15 and group 18 will have positive enthalpies compared to the rest of the group. Okay, in the period, along the period. Understood? So for the second period, the element beryllium, then nitrogen, beryllium, and is it nitrogen? Uh, yeah, beryllium and nitrogen and neon, they will have a higher electron gain enthalpy. Beryllium, nitrogen, and neon. Why beryllium? Because it has a completely filled 2s2 orbital. Okay. Similarly, why nitrogen? Because it has an electronic configuration of 2s2 2p3. So 3 electrons in the p orbital, thus a higher electron gain enthalpy. Next, neon, obviously, because it is stable, it is completely filled, it has a packed outer shell, therefore it also has stability. Now, moving along a group. On moving down a group, the size of the atom usually increases, right? So basically, you have lithium, beryllium, lithium, sodium, potassium, rubidium, cesium, francium. So the distance between the nucleus and the outermost shell is increasing as we go down the group. So the size of the atom increases, the electron gain enthalpy decreases. Understood? As the size of the atom increases, the electron gain enthalpy actually becomes more and more and more positive. Clear? Is it understood, Drupad? Clear? Okay, let's move on. Now, exceptions. The electron gain enthalpy of the second period nitrogen, oxygen, and fluorine is less negative than the succeeding elements of your the, ele- the, ele- the electron gain enthalpy of elements of the second period nitrogen, oxygen, and fluorine is less negative than the succeeding elements of phosphorus, sulfur, and chlorine in the third period. Okay, now I'll explain to this why this is happening. Now, we know that as we go down the group, the shell size increases, right? The shell size increases as we go down the group. Is there any doubt in this statement? As we go down the group, there is an increase in shell size. Now, if the shell size is increasing, okay, we can say that the group 2 elements will have the smallest shell radius, and the group 15 group basically um, the last group will have the when I'm saying the last, basically I mean vertically. Okay, the elements in group 2 will have a much smaller radius compared to the elements in the third period. Second period lesser radius, third period more radius, right? Am I right? Okay, now imagine this. Imagine you are driving a Maruti 800. That was my dad's first car, Maruti 800. Okay, it's a small car. It's an economic car. It's a small car. It is a legend in India, basically. Okay, so in that small car, if you can sit four people comfortably. Okay, four people can sit comfortably in that Maruti 800. If you try to increase the number of people in there, people will fit. There are times when my dad used to take us to trips where basically we used to cram ourselves like 7 or 8 people in that Maruti 800. We used to basically, we were small back then. Okay, we used to basically live, even then also we were comfortable. But the thing is, the space is less for more number of people in that small car. But if you have a big car, nowadays you have huge cars in India. Okay, massive cars, 7-seater, 10-seater. Okay, 10-seater cars. So more number of people can easily accommodate themselves in that car. Right. So the same logic has to be applied for the electrons in the the orbit of the second group, second period and the third period. Second period has a smaller what surface area. It's a shell, right? It has a smaller surface area. So the electrons that are present in the second period, second shell, have less space for accommodation. Therefore, if you try to add an extra electron in this cramped space, what ends up happening? The electrons that are already present in the shell, they will try to repel the incoming electron. They will try to push the incoming electron, even if they are in the 16, 17, 18 period, where you already have very high electron gain enthalpies in the negative direction, in the negative this thing. Even though that is happening, because of the cramped size of the second period elements, the cramped size of the valence shell, the incoming electrons feel a slight repulsion. But as we go to the third period, now what is happening? The shell size is bigger. Because the shell size is bigger, the electrons do not feel cramped. Okay, they feel less repulsion from the electrons that are present in the valence shell of the atom in the from the beginning. Okay, so therefore you will not experience more repulsion. Therefore, you will be easily able to accommodate an extra electron. Therefore, the electron gain enthalpy will be more negative. Clear? That is the reason why the even though we know that as we go from top to bottom along a group, the ionization, the electron gain enthalpy becomes more and more positive. That is, usually it should be positive, but the electron gain enthalpy of group 2 elements, sorry, period 2 elements, period. Why am I making this mistake? Period 2 elements is much more higher than that of period 3 elements. Okay, so that is the reason why nitrogen, oxygen, and fluorine have less negative, electron gain enthalpies compared to that of phosphorus, sulfur, and chlorine. Understood? This is an exception that you need to understand. Just when you are trying to describe this answer in your paper, you can imagine a small car, a large family trying to cram their people in that car. Okay, understood? Did you understand the logic what I'm trying to tell you? Is it clear? Okay, let's move on. Now, this is the same question. Which of the following will have the most negative electron gain enthalpy and which is the least negative electron gain enthalpy? You have phosphorus, sulfur, chlorine, and fluorine. Okay, so we know that phosphorus. So basically, phosphorus, we know that it is basically most negative. When we go from left to right across a period, the electron gain enthalpy becomes more and more negative. So phosphorus, sulfur. Phosphorus will have the more positive electron gain enthalpy compared to sulfur, and then it will be fluorine then chlorine. Okay, it will not be chlorine and fluorine, it will be fluorine and chlorine because of this explanation, because of the smaller surface area that they have in the outermost shell for fluorine compared to chlorine. Therefore, chlorine will have more electron and more negative electron gain enthalpy. Did you understand the logic behind this question? Clear? Okay, let's move on. Electronegativity. Just 1 second, okay? So the next topic that we have is electronegativity. What is electronegativity? Electronegativity is the property of an atom to attract shared pair of electrons towards itself. You know what a covalent bond is, right, Drupad? A covalent bond is a bond formed by two atoms who have agreed to share electrons with each other. Right? That's the basic definition of a covalent bond. Now, what is happening here? A quantitative measure of the ability of an atom in a chemical compound to attract the shared pair of electrons towards itself is known as electronegativity. Let us look at the example of hydrogen chloride. Okay, hydrogen chloride is nothing but HCl which is not present in water. When HCl is present in water, we call it hydrochloric acid. Otherwise, it is simply hydrogen chloride. Now, hydrogen chloride, how did it form? Hydrogen was lonely, chlorine was lonely. Okay, hydrogen wanted one electron to become stable, chlorine also wanted one electron to become stable. So they both made an agreement. They said, you want one electron, I want one electron. Let's both place the electrons in the middle and then let us share the electrons with each other so that you can make me stable and I can make you stable. So together we can make both ourselves stable. Okay, that was the agreement onto which the chemical bond was formed. But chlorine is a little bit selfish. Okay, chlorine is a little bit of a selfish atom. What does it do? Instead of following the agreement made by them during the formation of the chemical bond, chlorine tries to sneakily bring the electron pair closer to itself. For example, in the case of hydrogen and chlorine, there is a double bond. There are two electrons being shared here. I'm going to show you where the electrons actually stay. The electrons should have stayed in the middle. Okay, they should have stayed in the middle like this, but they don't. They stay much closer to the chlorine atom. Okay, much closer to the chlorine atom compared to that of hydrogen. Now, even though the chemical bond or the covalent bond is being formed between a hydrogen and a chlorine atom because of the selfishness, the selfish act that chlorine is doing in this situation. Hydrogen attains a slight positive charge. It is not plus one positive charge. That is what you need to remember. It is not plus one positive charge as in the case of ionic compounds. It is a slight positive charge. Okay, and chlorine attains a slight negative charge because electron hasn't lost, sorry, hydrogen hasn't lost this electron. Chlorine hasn't stolen this electron. They are both still sharing, but the sharing is unequal, due to which what happens? A covalent bond shows ionic character. A covalent bond is showing us ionic character. What is an ionic character? When you have cations and anions in your molecule, in your this thing, in your lattice, then you call it an ionic character. So even though a covalent bond is being formed between these hydrogen and chlorine atoms, you have ionic character present in them, and that is known as what? Polar. This becomes a polar molecule. Water is a polar molecule. Again, water has a chemical structure something like this. Okay, so oxygen is a little bit selfish compared to that of hydrogen. So instead of sharing the electrons in the middle, the oxygen atom basically brings the shared pair of electrons closer to itself, due to which what happens? There is a slight negative charge on the oxygen atom and there is a slight positive charge on these two hydrogen atoms. So we say that a covalent molecule has attained ionic properties. Therefore, we call them polar molecules. Okay, that's where polar molecules actually comes from. Understood this, Drupat? Is there any doubt here? Did you understand? Exactly, exactly. Covalent bond is having ionic properties because of the selfish character of chlorine, because of the selfish character of oxygen. They are, because see, if the electrons were exactly in the middle, then you would not see this ionic character, this polarity. Polarity means what? Having poles. Poles are what? You cannot have two poles of the same same this thing direction. Okay, you can either have a north pole and a south pole. That is what polarity means. You can have a positive charge and a negative charge. That is what polarity means. Polarity means having two opposites of equal magnitude but opposite direction separated by a distance. Okay, that's what polarity means. Two quantities having the same magnitude but opposite direction separated by a distance. Understood? You can see that it has a positive plus delta and a negative delta. The magnitude is the same in both our cases. Only one is becoming positive, the other is becoming negative. That is what polarity actually means. We will learn more about this in the next chapter, where we learn that we will learn something known as the covalent character of ionic bonds. Ionic bonds show covalent character. Covalent bonds show ionic character. Okay, that is something that we have to understand. That is something we have to come into terms when we are discussing about chemistry. Understood? Especially the molecular nature. Clear? Drupad, is it clear? Is it absolutely clear? Okay, let's move on. So, other properties such as electron gain enthalpy and ionization enthalpy, which are related to the isolated state of an atom, electronegativity is related to the combined or the bounded state of an atom. In general, greater the electronegativity, higher is the tendency to attract the shared pair of electrons. Since this tendency is highest, it is the highest in fluorine. It is the most selfish atom in all of the periodic table. Fluorine is the most electronegative or most selfish atom. Okay, clear? This whole thing is clear. So, who is the most electronegative element in the periodic table? Fluorine is the most electronegative element in the periodic table. Okay. Further, noble gases, because of their stable state electronic arrangement, do not exhibit any electronegativity. They are like monks. Okay. They are like sadhus who do not have any selfish behavior. Okay. They do not interact with people. They are isolated. They do not interact with any other compound. They are exactly like the sadhus. Okay. They are like the monks of the periodic table. They do not mind what other people are doing. Fluorine, most selfish, is the most selfish atom in the periodic table. Your noble gases are the least selfish. They do not care about anybody. Okay, they only want to stay isolated. Clear? Done? Okay, let's move on. Factors affecting the magnitude of electronegativity. There are various factors which affect the magnitude of electronegativity and are as follows. Now, there is a huge difference between your ionization enthalpy, electron gain enthalpy, and your electronegativity. Ionization enthalpy and electron gain enthalpy was the property of the atom itself. It was not a relative number. But electronegativity has a different story altogether. So, how selfish are you depends on the opponent who is going to combine with you. If you have a person who is willing to donate everything and you have a person who is selfish and willing to accept everything, then you have a different electronegativity. The electronegativity changes with the change in partners. Okay, electronegativity is usually found in covalent molecules, in your this chemically bonded molecules. That's where you see the electronegativity. But electronegativity is not something that is what do you say, that is dependent on the atom. It is dependent on the group as a whole. How much of this character can be attained, it depends on the group as a whole. Okay, every single, so if you want to find the electronegativity of a single atom, you won't be able to do that. You will only be able to do that with different atoms. Okay, we'll learn more about this now in just 2 minutes. The atomic radii. Okay, as the atomic radius of the element increases, the electronegativity also does what? The electronegativity decreases. So as we move down the group in a periodic table, because the atomic radius is increasing gradually, what happens? The electronegativity also becomes less. So in the case of the halogens, fluorine, chlorine, bromine, iodine, astatine. Okay, astatine is less electronegative, is the least electronegative in the halogen family, and fluorine is the most electronegative in the halogen family. It literally looks like this. Okay, fluorine, astatine. Understood? So, increase in size, decrease in electronegativity. Next, effective nuclear charge. The electronegative value increases as the effective nuclear charge on an atom's nucleus increases. How? See, nucleus is the one that is attracting the electrons. Okay, the nucleus has the power to attract electrons. So, if your effective nuclear charge is large enough, then you will be able to bind the electrons, bring the shared pair of electrons towards yourself. Okay, because nucleus is the one that is attracting the shared pair of electrons. Okay, so the more effective nuclear charge you have, the more electronegative element you are. Next, oxidation state. The electronegativity increases as the oxidation state increases. What is oxidation state? The loss of electrons makes you oxidized. Okay, the less number of electrons you have, the more electronegative you are. Why? Because if you have, see, if you had the same number of protons and the same number of electrons, you would be considered neutral. But if you have more number of electrons, if you have more number of electrons, sorry, if you have less number of electrons, that is, you are oxidized, your overall positive charge, the effective nuclear charge is higher now. Since the effective nuclear charge is higher, it becomes easier for the atom to act even more selfish. It will basically bring the shared pair of electrons towards itself much more effectively. Understood? This is what is happening here. Okay, the positive charge, the overall positive charge on the atom is making sure that the shared pair of electrons are closer to the more selfish atom. So the increase in oxidation state increases the electronegativity. Next, did you understand this, Drupad? Okay, next, your hybridization. What is hybridization? So, in chapter number 2, structure of an atom, you understood that there are four different types of orbitals. There is an s orbital, there is a p orbital, there is a d orbital, and there is an f orbital, right? There are four orbitals that we have: s, p, d, and f. Now, in the next, when we learn Vesper theory, okay, valence shell electron pair repulsion theory, or molecular orbital theory, or hybridization. In all these theories, we will learn something known as hybrid orbitals. Okay, what are hybrid orbitals? Now, for an isolated atom, usually what we see is that the orbitals are at their exact same location. Now, but if you want to combine yourself with another atom, you cannot just use one orbital. You will have to use multiple orbitals. Okay. Like basically, if it's a single bond, obviously you will use one orbital, but it is always preferred to use multiple orbitals. Okay. Sorry, these multiple orbitals, how are they formed? They are formed by the overlapping of sp orbitals. So if an s and a p orbital overlap, you get the sp hybridization. If s and 2p orbitals overlap, you will get the sp2 hybridization. Similarly, an sp3 hybridization. If s, p, and d orbital overlap, you will get sp3d hybridization. sp3d2 hybridization. We are going to learn much more about this in the next chapter. For now, all you need to remember is the S character. Okay, so you know now, just keep this in your mind, that the S character is what? The S orbital's character in the hybrid orbitals. Hybrid orbital is a mixture of multiple orbitals coming together, overlapping with each other to form a hybrid. Okay, if the S character in a hybridization state of an atom increases, the electronegativity also becomes increases, because s electrons are comparatively closer to the nucleus. Okay, so as the s character in the hybrid orbitals increases, the more electronegative the atom becomes. Okay, this is something that we will understand much more deeply when we study the chemical bonding chapter. Okay, we will do that probably next week. Next, nature. Did you understand this? Okay, you don't have to understand this completely. You will understand more about this in the next chapter. Okay, for now, just remember, as the S character increases, the electronegativity also increases. Finished. Clear? Okay. Nature of substituent attached. The electronegativity of a group also varies with the nature of the substituents attached. This is due to the inductive effect of the substituent group. So, CH3, CCl3, and CF3. CH3 has an electronegativity of 2.3. CCl3 has an effective electronegativity of 3.3. CF3 has an effective electronegativity of 3.35. I'll explain to you why this is happening. Okay, now CH3, how will you draw? You will draw it like this. Okay, this is due to the inductive effect of the substituent group. Electronegativity of carbon is adjusted by the presence of substituents CH3, Cl3 and 3F atoms. Okay, look at this. This carbon is surrounded by 3 hydrogen atoms. Okay, this carbon is surrounded by 3 hydrogen atoms. We are going to learn something known as the inductive effect. What is an inductive effect? Now, basically, there is an electron cloud that is present around this carbon atom. Okay, there are electrons that are present in around the carbon atom. We call it the electron cloud. So, hydrogen has an inductive effect where it basically gives its electrons, okay, to the carbon atom. It just gives it. It basically transfers its electrons, not completely though, but it provides enough electrons to this carbon atom to reduce its hunger, to reduce its selfishness, to reduce its electronegativity, so that this carbon atom does not take more number of electrons from anything that is attached to it. For example, let us CH3Cl. Okay, so CH3Cl, the shared pair of electrons will be closer to the chlorine atom because of these 3 hydrogen atoms. These 3 hydrogen atoms are constantly giving off their hydrogen to this carbon, thus increasing the electron cloud, thus increasing the strength of the electron cloud, thus reducing the hunger for carbon. Okay, that's why the carbon has a lesser electronegativity. But now look at the other one. Okay, CF3. Okay, CCl, Cl, Cl. Okay, now in this case, what is happening? These chlorine atoms are more electronegative compared to that of your carbon. So, the electron cloud that is present around this carbon is being attracted. It is being attracted by these 3 chlorine atoms. Okay, so now what is happening? Carbon had some amount of food with it. Carbon had some amount of electrons with it. But the selfish chlorine atoms have taken that from it. They have taken the electron cloud from the carbon atom. Okay, they have just taken it for themselves. Not completely though, but to a much larger extent. Now, what is happening here? Now, this carbon atom is now more electropositive. The effective nuclear charge has increased because it is lacking electrons. The closeness that the electrons were, the initially before the chlorine atoms were attached, the electrons were much closer to the nucleus. But now, because of these chlorine atoms, the electrons are much further away from the nucleus. Therefore, what happens? The overall positive charge on the carbon atom has now increased or shot up. Therefore, this carbon atom with its newfound positive charge, partial positive charge only, it is now able to attract the electrons in whichever molecule it binds with, much more closer to itself. Okay, so the overall electronegativity of this carbon atom has now changed. The same carbon atom has now become more selfish when it is surrounded by chlorine. See, that's why I said electronegativity is not an isolated event that you can study by just studying the atom itself. You have to realize who is the atom is connected to. Now, in case of fluorine, think about this. Fluorine is the most electronegative, most selfish atom in the whole of the periodic table. Right? It is the most selfish atom in the whole of periodic table. So what ends up happening? The electron pair, the electron pair is now even closer to the fluorine atom. The carbon atom has become even more positively charged. So basically its electronegativity has shot up to 3.35. Clear? So, thus, the nature of the atoms or the substituents that are attached to the central atom also has an effect on the effective nuclear charge. When it was hydrogen, the electronegativity was low. But in the case of chlorine and fluorine, the electronegativity has jumped by one whole unit. Are you able to understand what I'm trying to say? I know it's a bit of a complicated topic, but you have to understand, if you think of these elements as people, you will be able to understand their nature much more clearly. Think of fluorine and chlorine being more selfish than carbon. Carbon is more selfish than hydrogen. That is why in the case of CH3, carbon was able to attract the shared pair of electrons that it had agreed to be shared between carbon and hydrogen. Therefore, carbon in the case of CH3 is less electropositive. In the case of chlorine and fluorine, the carbon atom has attained a higher electropositivity, thus being more selfish, thus being more electronegative. Understood? Okay. See, Drupad, like I'll give you another explanation. Okay. If you have good friends, okay, if you have good friends with you and you forget to bring your tiffin to school, what happens? Do you stay hungry? No, right? Your friends will share their meal with you. They will say, oh, I am already full, you can have some of mine, and then they will share the food with you, so you will not be hungry. You will not want to buy food from the canteen, or you will not want to steal the food from someone else, because your hunger for food is basically being compensated, is being filled, is being fulfilled by the people around you. So you are not selfish anymore, you are not hungry anymore, you are not electronegative anymore, right? You are less electronegative compared to before. But now, if you have selfish friends, like basically you brought tiffin from your house, okay, you brought tiffin from your house, your mom made some good food, and then your friends just stole your tiffin and ate it and placed it back in your bag. Now you would be forced to buy something from the canteen, you would be forced to basically steal the food, okay? So basically, this is how electronegativity works. It basically depends on who is attached to you. If someone good is attached to you, you are less electronegative. If someone bad is attached to you, you become more electronegative. Understood? Did you understand with this logic? Is this logic much more clearer? Okay, let's move on. So, electronegativity is not a measurable quantity. So several numerical scales of electronegativity of elements vis-a-vis the Pauling scale, the Mulliken's Jaffe scale, the Allred-Rashov scale has been developed. We are only going to be interested in the Pauling scale. Okay, so what is the Pauling scale? This will be the last topic for the class. Okay, we will be able to finish this off in the next chapter, and then we'll move on to the next chapter in the next video. Okay, the Pauling scale. Let us understand how we can calculate the electronegativity of a chemical bond using the Pauling scale. Drupad, this is I think one of the only numerical problems that they can ask you from this chapter. So open your ears and please understand. If you have any doubts in this section, please do ask, because this is the only numerical in this chapter. That's it. No other numerical exists in this chapter. Okay. So it is the most widely used scale and was proposed by Linus Pauling, an American scientist, in 1922. He arbitrarily assigned a value of 4 to the most electronegative element, fluorine, and calculated the electronegativity of other elements with respect to fluorine. Okay, because fluorine was the most electronegative element, they assigned -2 to it. Sorry, they assigned 4 to it. That is, 4 is the largest electronegativity that you can have in the Pauling scale. Okay, 4. Understood? 4 is the electronegativity of fluorine. He fixed it. And then he tried to figure out how much electronegativity other atoms and elements have compared to fluorine. Is this logic clear? This is clear, right? This is 100% clear. Okay. Next. Now the formula that he used was XA minus XB is equal to 0.1017 root under delta. Okay, where XA and XB are what? They are the atoms. They are the electronegativities of the other atoms. Okay, so if the bond dissociation enthalpy is in kilojoules per mole, if it is in calories, you use 0.028. Okay, so 0.1017 for kilojoules per mole or 0.208 in the case of calories, because if you multiply this thing, you will get the kilojoules per calorie, kilocalorie per mole. So this is the two formulas that you need to remember. One more formula is there which is called the delta. We'll observe what delta looks like. What is the meaning of delta? Delta is what? Delta is the what? EAB minus root under EAA multiplied by EBB. XA minus XB. What does it mean? XA minus XB is the electronegativity difference between the two atoms A and B. XA represents the electronegativity of the element A. XB represents the electronegativity of the element B. So the difference between their electronegativity is equal to 0.1017 root under delta. Now, what is EAB? EAB is the bond energy of the molecule AB. How do you find the bond energy of a molecule AB? The amount of energy required to break the bond is known as its bond energy or the bond enthalpy. Okay, bond enthalpy, if it is high, what does it mean? It means that the two atoms are attached very tightly. If the bond enthalpy is low, it means that the two atoms are not attached tightly enough. Understood? Is this point clear? Hmm? So basically, EAB is the bond enthalpy between A and B. EAA is the bond enthalpy of the A2 molecule, and EBB is the bond enthalpy between in the B2 molecule. Now, the electronegativity values for some elements on the Pauling scale are shown in the following table. Electronegativity for group 1, group 2, group 13, 14, 15, 16, 17. So, you need to remember these two formulas to calculate the electronegativity. Electronegativity of the representative elements. Who are the representative elements, Drupad? Who are considered to be the representative elements? No. The S and the P, da. They are the main or the representative elements. They are the people who represent the periodic table to the world. Okay. D is known as the transition series. Okay. F is known as the inner transition series. Okay. Now, electronegativity of the representative elements. The main disadvantage associated with this scale is that for many elements, the bond enthalpies are not known with good degree of accuracy, and hence the enthalpy values are only the relative values. Okay, let's actually do a question and try to understand how to use this formula. Calculate the electronegativity of carbon if the bond enthalpy of hydrogen is 104.2 kilocalories per mole. Bond enthalpy of carbon and carbon is 83.1 kilocalories per mole. And the bond enthalpy of carbon and hydrogen is 98 kilocalories per mole. And the electronegativity of hydrogen is 2.1. So we know that the formula is what? XA minus XB is equal to 0. Because they are given in calories, we'll use 0.208 root under what? EAB minus EAB minus root under EAA multiplied by EBB. Okay, so this is the formula that we have. So we need to find the enthalpy of XA, that is X of carbon minus X of hydrogen should be equal to 0.208 root under the bond enthalpy between carbon and hydrogen minus the bond enthalpy of carbon multiplied by the bond enthalpy of hydrogen. So we know the value of XH, right? So XC is equal to XH, XH is XH plus 0.208 root under ECH minus root under ECC multiplied by EHH. So X of C is equal to what? 2.1 plus 0.208 root under what is ECH? 98.8 minus root under 104.2 multiplied by 83.1. 83.1. Okay, now if you solve this whole thing, if you solve it, what will you get? You will get 2.6. Okay, by solving this whole complete formula, you will get 2.6. So what is the formula that we have? XA minus XB. The electronegativity of A minus the electronegativity of B is equal to 0.208 for kilocalorie or 0.1017, right? 1017, yes. 1017 root under EAB, the bond enthalpy of AB minus the bond root under bond enthalpy between AA multiplied by the bond enthalpy between BB. Okay, this is known as the Pauling formula. This is known as what? The Pauling formula. Is it clear how we can calculate the electronegativity of any species if we know the values of EAB, EA, EB and XB? Four values are required. Four different values are required to use this Pauling formula. Remember this in your head. If they are giving you four values of the basically any of this XA or XB, if they're giving you, and EAB, EAA and EBB, if they're giving you, you can use the Pauling formula to calculate your answer. Is this clear, Drupad? Is the Pauling scale actually clear to you? Okay, so this will be the last topic for us today. Okay, so students, I hope you really liked this video. Okay, in the next video, we will complete this chapter and we will move on to the next chapter of chemistry, chemical bonding. If you really like my video, if you like my explanation, please do like, share and subscribe. If you have any doubts, if you want me to make a specific video on a certain topic, do put on the comments and I'll try to make the video as soon as possible. Okay, so your half yearlies are going to come very soon. So all the best for your half yearly exams and I'll see you in the next video. Bye.